Hello and welcome back, everybody. Today in not calculus, in geometry, we will be talking about corresponding angles and how are they related to the parallel lines that we've been working with. Previously, we defined what is a parallel line, and what are two parallel lines then, and also what are alternate interior angles. So in this section, we're going to go ahead and sneak this one in, which is called the corresponding angle. Okay, so we're going to go ahead and define the corresponding angles first, and then afterwards, we're going to create a theorem that is called corresponding angles will allow you to show that two lines are parallel, assuming that those two corresponding angles are congruent. All right, so here it is. Definition first. Corresponding angles, or CA for short if you would like. So in the picture right here, which I'm going to explain in just a little bit, two angles that are corresponding angles if they are on the same side of the transversal, non-adjacent, and one of them is in the interior of the other. So you have a picture that's on the right, and you can see that there are 8 angles that are formed. So first off, I'm looking for 2 angles that are on the same sides. So that means that the same side of the transversal. So that means I'm looking at maybe like say 1, 2, 5, and 7, or 2, 4, 6, and 8. So I'm just going to go ahead and choose one of the side for the time being. So 2, 4, 6, and 8. Now to eliminate some of these right here, I need to make sure that those are not adjacent. So if I'm looking at angle 2, then I am definitely not looking at angle 4. So I'm going to go ahead and make a quick erasure of that part right here to eliminate that. So that means now if I have angle 2, then either angle 6 or angle 8 is going to be the corresponding angle. Then the final part is that the two angles, one would have to be inside the interior of the other. If you draw angle 6, you can see that angle 6 is going to be, all of this region over here. So you can see how angle 2 is in the interior of angle 6. So that makes 2 and 6 to be the corresponding angles then, whereas 8 is on the opposite side and it doesn't work out. So in conclusion, 2 and 4, those are going to be corresponding angles. Now, are there other corresponding angles? The answer is yes, because you can definitely see, according to like kind of like a pattern, that there are 4 pairs of corresponding angles. So to just kind of start off with, we can say that 2 and 6 are going to be corresponding angles. We can also say that 1 and 5 are corresponding angles. And then 3 and 7 are corresponding angles. And finally, 4 and 8 are also corresponding angles. So I think that's probably an easier way to show it. Corresponding angle is one of those things where it's easier to show than it is to kind of define. But nonetheless, there you go. Now, as we said, you can see how alternate interior angles and corresponding angles are kind of similar to each other because, if they have some sort of relationship to each other, the corresponding angles or the alternate interior angles, then we can say something about the lines that are going to be formed by them. In the last section, we said that if the alternate interior angles are going to be congruent, then the two lines are going to be parallel. Well, in the case of corresponding angles, I'd like to think that there's going to be the same thing then. So that is going to be our theorem 9.7. So just jumping straight into the one that is important. That's why it's in red. So CAP for short. So that means that corresponding angles implies that parallel lines is what you actually have. So in this theorem, it says that given two lines are cut by a transversal, if a pair of corresponding angles are congruent, then the two lines given are parallel to each other. So as a restate, that I am given angle 2 is congruent to angle 6. So you can see how they are parallel, they are corresponding angles. And what I would like to do is prove that line 1 is going to be parallel to line 2. Well, if you think back to what we did in the last section, the way we proved parallel is that we said, okay, let's go ahead and assume that the two lines are not parallel to each other, and therefore they create some sort of intersection. So basically, just doing some sort of indirect proof then. So here, let me just kind of write that out over here first. So we're going to do an indirect proof, okay, by assuming that L1 and L2 are going to intersect each other, and we're going to go ahead and call that intersection, let's say point X then, okay? So we're going to go ahead and see if we can try to draw that here just to make it so that you can see where that point X is. So let's say that L1 is coming down this way, and then L2 is going to go up this way so that they actually intersect each other at point X. So this is kind of like my like weird L1, that's according to the assumption, and this is going to be the weird L2 then. Now notice the location of 2 and 6. Now if I were to just draw the red, so then that way you can see it without the blue, 2 is located over here and 6 is located over here. And you'll note that just like in the last section where I messed up the proof, 2 and 6 are, 1 is an exterior angle and 6 is an interior angle, right? This guy right here, this is an exterior angle, and this is going to be a remote interior angle. And by the theorem of exterior angle theorem, we know that 2 has to be greater than 6. But according to our given, 2 is congruent to 6. So there is going to be our contradiction, and that's why it's impossible for line 1 and line 2 to intersect each other. But there you go. That's the easy part then, okay? So now let's go ahead and maybe do a proof with all of these AIP and CAP, so then that way you can see how that actually works out. So as of right now, we have 2 new ways of proving that you have lines that are parallel. We have alternate interior angles, and then that proves the line parallel, so we'll call that AIP. Whereas you have corresponding angles, and that also prove corresponding angles, if they are congruent to each other, then the lines are going to be parallel too, so we'll call that CAP then for short. So here in sample number 1, what I'm giving you is the following figure and the following given over here. We know that SX is going to be equal to UV. We have XW is going to be equal to TU. And then finally, we have ST, which is going to be equal to WV. What I would like to do is prove that XS, the line, is going to be parallel to UV, the line. Well, to draw in what I have right here, SX is equal to UV, so that means that these two are going to be congruent to each other. XW is going to be congruent to TU, so that means these two are congruent to each other. You can kind of see what's being formed here. We're trying to show that these two triangles are most likely congruent to each other. And finally, ST is going to be congruent to WV, which is over here. Now note that TV is not involved, so I'd like to probably get that in there somewhere. But according to my picture, it definitely looks like the two triangles are going to be congruent to each other by SSS. And if that's the case, then maybe we can use corresponding parts to show that angle S is going to be congruent to angle V. And if you notice their position, SV is the transversal to SX and also VU. So that means by AIP, the alternate interior angle, I can prove that those two lines are going to be parallel. All right, so here, let's go ahead and write down the proof right here. So you can see that I did it for you just to kind of kill some time or speed things up. So first, we're going to go ahead and say that the third part, we say that the ST is equal to WV. So this is congruent to this. Next, I'm going to add in the part that they're missing. So that is going to be the addition property of equality, adding in TW to both sides. We then say each side is equal to the entire length of its respective sides. And then that is going to be my segment addition postulate. And by replacing the left-hand side and the right-hand side with the entire segment, then we can now say that SW is equal to TV, which is really what I want for that side anyways. So right there, that proves the side part of my SSS. The other two, well, that's easy because that's given. So those are going to be just written down as is. So we have SSS now. We can say that the two triangles, as we said, are congruent to each other. And now the corresponding part I want is the angle S is congruent to angle V. So here is angle S, here is angle V. And you can see that by their location, they are alternate interior angles. And since, according to what we just did, we proved that the alternate interior angles are congruent, so therefore the sides or the length over, the segment over here and the segment over here, the two lines that are going to be formed by those angles, but not the transversal, are going to be parallel to each other. So finally, XS is going to be parallel to UV by AIP then. Okay. All right. Now here's the last one. Here's the last sample problem, which actually turns out to be a theorem, but we'll just go ahead and look at it as a sample problem anyways. Given that 2 and 3, the angles are supplement to each other. So that means that this guy right here is going to be supplement to this guy right here. What I would like to do is use that to prove that line 1 and line 2 are going to be parallel to each other. Now, as I said, normally we would prove by using some sort of contradiction or indirect proof, but now that we have AIP and CAP, I would like to utilize that if possible. Well, this time around, I'm going to go ahead and write the proof in paragraph form just to give you a different variation. And again, in your homework, you can go ahead and use either way. You can write it in statement and reason, or you can go ahead and write it in paragraph form, just like in this case. But whereas, if statement and reason like above right here is easier, then go ahead and stick with it. So here's what I'm noticing just before we kind of get the whole thing started. I'm noticing that if you look at angle 2, right, and angle 1, they are going to be linear pairs. And if they are linear pairs, then that means that they are supplement to each other. So if angle 2 is supplement to angle 1, and angle 2 is supplement to angle 3 because they're given, then by the supplement theorem, 1 has to be the same as 3. Because there was the supplement theorem from back in chapter, I think it was like 3 or chapter 4. Well, if 1 and 3 are congruent to each other by the supplement theorem, they are corresponding angles, and then therefore line 1 and line 2 are going to be parallel to each other. So here, let me just go ahead and kind of reiterate what I said as a paragraph. We know that angle 2 and angle 3 are supplementary to each other because that was given. Angle 1 and angle 2 are supplement as well because they form a linear pair, just like it says in the picture. Then we say angle 2 is congruent to itself by the reflexive property. Do you necessarily need that? Not necessarily, but I'm just trying to set up everything that we have for the supplement theorem. And I need to have something about if two angles are congruent, then their supplements are going to be congruent. And that's why that's there. So therefore, angle 1 is equal to angle 3 or congruent to angle 3 by the supplement theorem. And then by CAP, then line 1 is parallel to line 2. And there you go. That's pretty much it. All right, well, there you go. Pretty short lesson. Thank you so much for watching, and I will see you next time. Have a good one. Bye-bye.